Great. So our third fellow this afternoon is Abigail Poteshman. Abigail comes to us from the University of Chicago, where she was in computational and applied mathematics. Her advisor is Julia Ghali. Abigail wins the award this afternoon for having completed 3 practicums. One, the first at Lawrence Berkeley, and then 2 more at Argonne, both at Argonne National Lab. Abigail, the floor is yours.
Thank you for the introduction, and today I'm going to talk to you about some research that grew out of my first practicum at Berkeley, and this is on accelerating spontaneous polarization calculations. So first, what is spontaneous polarization? Spontaneous polarization is a phenomenon that we observe in crystal materials, where materials are made up of positive and negative charges from atoms. We have positive charges from nuclei and negative charges from electrons. Most materials are in a nonpolar phase where there's a high degree of symmetry. So on average, the positive and negative charges cancel out and we get an electrically neutral material. In polar materials, which is what we focus on, there is some sort of distortion or asymmetry in the configuration of atoms such that now there isn't this cancellation of charges and you end up with a material with an electric dipole moment, even in the absence of an externally applied electric field. And for these polar materials, we observe this because they're at a lower ground energy than their symmetric counterpart. And we care about computing spontaneous polarization because if we know the spontaneous polarization, we can then compute the magnitude of an externally applied electric field we can use to then switch between these 2 different polar configurations. And this switching property is important in many different applications, some of which are listed here. And our goal is to be able to calculate spontaneous polarization quickly and in an automated fashion. And our goal for being able to do so is really twofold. First, we want to be able to identify new candidate polar materials for specific applications using high-throughput computational screening. And we also want to be able to generate a large volume of accurate, high-quality training data for machine learning models to better understand this structure-property relationship. And to compute polarization, we consider contributions from both the nuclei and the electrons. The nuclear contribution can be written as roughly the charge times the displacement of the nuclei, and we can write the nuclear contribution like this because we approximate the nuclei as classical objects, so their location is well known. And this contribution is trivial and fairly straightforward to compute. In contrast, for electrons, because they're quantum mechanical in nature, so they aren't necessarily well localized, to find an electronic analog for displacement, we have to use a difference in these objects called Berry phases, and this is really challenging and non-trivial to compute. So the rest of this presentation is on trying to explain why this difference is challenging to compute and how we address these challenges. So Berry phase is defined as a function of periodic electronic wave functions at a series of k points. And to explain how we obtain these electronic wave functions, I'm going to take a step back and just give a very, very poor description of DFT. But essentially, we start with a unit cell of a material of interest, and we simulate this with periodic boundary conditions. We apply a discretization mesh in reciprocal space. And then at each of these k points in reciprocal space, we obtain an electronic wave function that describes the probability of where this electron is located. And this electronic wave function can be written in terms of an amplitude and a phase. However, there are many different ways we can write down a physically valid wave function, and these different ways of writing down these wave functions are called gauge transformations. And so one such gauge transformation is if we have an original wave function, we can apply arbitrary factors of e to the negative I2 pi and end up with a slightly different way of writing a wave function that corresponds to the same physical distribution of charge. And the key point here is that Berry phase is not invariant to gauge, meaning it matters when you do this calculation how you write down your wave functions. And in particular, if you have some wave function and you compute the Berry phase, and then you apply a gauge transformation to those same wave functions and recompute Berry phase, you're not necessarily going to get the same number. So as a result, Berry phase is defined not as a single number, but as a spectrum of numbers, where the different numbers correspond to the different possible gauge transformations of your wave functions. And also crucially, when we obtain our electronic wave functions at each k point, We know that at each k point, we have a physically valid wave function, but we don't necessarily know a priori which gauge they're written in. And so to kind of illustrate why this is challenging, I'm going to show some kind of toy examples of 1D point charge distributions. So we have this nonpolar phase where we have an even distribution of positive and negative charges. And now we can consider a polar phase where the positive charge is displaced relative to our original nonpolar phase. We simulate this by looking at one unit cell and applying periodic boundary conditions, and we can now compute an associated Berry phase. And now if we take the same charge distribution as the top, but we apply a gauge transformation where now we shift every single positive charge by exactly one unit cell, the distribution of charge is exactly the same when we look at our single unit cells. But now when we compute Berry phase, we might get a slightly different number. And my point is that when we take this difference, we have to be really careful about which gauge our wave functions are written in. And as long as our kind of relative offset is accounted for, when we take this difference amongst wave functions or Berry phases from wave functions in the same gauge, we get the correct answer. But we want to avoid taking differences between Berry phases written in different gauges, because then we'll get the wrong answer. And so going back to polarization, so our goal is, again, to compute this difference in Berry phase. And the way you would go about doing this is you would take your polar and nonpolar phase unit cells, you would compute your electronic wave functions, you would obtain a single Berry phase from whatever gauge those wave functions are written in. You would then compute all of the symmetry-related Berry phases. And now the task is you want to take a difference between some points on this line and some points on this line, but you don't know which sets of points to correspond to each other. So, whoops. For example, here are two different possible ways you could align these points, and the challenge that we're trying to do is which of these 2 points should we take the difference between. And mathematically, this is the same problem as if I asked you to calculate how many days are between Monday and Wednesday without telling you what dates. It could be 2 days, it could be a week and 2 days, it could be n week and 2 days. If you shift both days by the same relative amount, that difference isn't going to change. But if you start shifting your different days by different amounts, that difference will change. And the way that this is typically resolved, and this is kind of the standard state-of-the-art method, is we associate these two, which kind of corresponding points are aligned, by creating a new set of structures by linearly interpolating the nuclear coordinates between your polar and nonpolar phase. For each of these interpolates, we compute the wave functions, we compute the associated Berry phases, we fill in the symmetrically related Berry phases, and we use this grid point to try to trace out the evolution of the Berry phase from the polar to nonpolar phase, and now we have correctly assessed which 2 points to take this difference between. And so my claim is that if you want to do this procedure for one material, this is fine. If you can kind of babysit all of the intermediate calculations, this is going to, roughly speaking, give you the right answer if you're doing it correctly. However, in terms of automation, this poses challenges. So going back to our original motivation to be able to do high throughput computational screening, this interpolation-based workflow is not so great. And one key point is that for each of these wave function calculations, this is really the computationally limiting step. There's a variety of different methods you can use to obtain these wave functions, but they're all slow and expensive. And when you actually go to automate this workflow, a priori, you don't know how many interpolations you need to resolve the branch. Bad things can happen in terms of the physics because these interpolated structures are in some sense fake. So you can get things that should be insulators becoming metal, and then this leads to a real breakdown in the formalism we're working with in terms of the physics. Actually designing a branch tracing algorithm from a series of grid points is non-trivial. And also knowing if you correctly selected the correct branch from a series of grid points is also kind of challenging. And so now I'm going to turn to the method that we've been focused on developing. And the key point is that we design a new algorithm that completely gets rid of having to use any interpolations. And so that's really why it's faster, because we remove a lot of the computationally limiting steps, and we're able to circumvent all of these different challenges related to interpolations. And so we're able to compute our Berry phase directly from our polar and nonpolar phases. And so again, this is the quantity that we're trying to compute, this difference. And the key idea is that if we can somehow enforce that every single wave function is written in the same gauge, we can then directly take this difference. So going back to our time analogy, this is saying if we want to take the difference between Monday and Wednesday, now we're going to fix Monday to a specific date, say July 14th, 2025, and now we're going to compute everything with reference to a specific date. And so again, here's our electronic wave functions. We can apply these gauge transformations, which again are related to this translational symmetry in our unit cells. Our charges can be displaced by exactly integer numbers of unit cells, and our charge distribution remains the same. And when we apply this gauge transformation, we observe that if we can figure out n, we can, in some sense, undo this gauge transformation by now multiplying by factors of e to the plus I to pi n. And so we can actually figure out n by taking the inner product of two wave functions related by a gauge transformation, and we exactly get out e to the I 2 pi n. So as a result, we can figure out n by taking the imaginary log of an inner product between two wave functions related by a gauge transformation. And we take this insight and say, okay, in our problem, if we can align the gauge of wave functions that are not exactly the same, but pretty close to each other, we can kind of extend this method to now align wave functions that are close together in space and propagate that out until all of our wave functions are gauge aligned. And to kind of quickly sketch what this looks like, we take our polar and our nonpolar phases. We have a series of k points, and we have wave functions at each of these k points. A priori, we don't know what gauge these are written in, and they could all be written in different gauges, and our goal is to write them all in the same gauge. We can do this by fixing a single wave function at a single k point, and then aligning all of the nearest neighbors in k space with our fixed wave function. And we can continue propagating out this nearest neighbor's gauge alignment until every single wave function in one of our structures is gauge aligned. And then we can kind of bridge between our two different k-point meshes by taking a wave function, two wave functions at corresponding k-points across our two materials and aligning them. And then similarly, using this nearest neighbors approach until all of our wave functions are gauge aligned. And once our wave functions are gauge aligned, we can now, with confidence, take this Berry phase difference without having to worry about if we're correctly taking the difference between the corresponding points. And so we implemented and tested this method on a variety of different materials. Here we have our gauge alignment method on the y-axis and a manual interpolation method on the x-axis. And we test both a bunch of kind of well-known standard polar materials. We also test the materials that previous attempts at designing automated workflows to compute polarization based on this interpolation-based approach have failed. And we've also looked at some materials that have some more sophisticated magnetic properties as well. And then back to my original claim, is it faster? Here we have just a few materials, and you can clearly see that our method vastly outperforms the interpolation-based method. And again, this is because we removed the computationally limiting step. And we took some care to try to make a fair comparison. And I would say that for these interpolation-based approach, we use 3 interpolations, which is really as few as you can get away with. Like, you don't want to interpolate between 2 points. And so this is kind of a best case interpolation approach, and we still really outperform it. And because we get exactly the same answer, but at much, much faster computational cost, I really think this is going to be the kind of new standard method to compute spontaneous polarization. So it was very exciting to work on that. And so to summarize, we have a faster method. It's faster because we removed the computationally limiting step. And we're kind of currently working on releasing this within the PyMagen infrastructure and all that. And we currently have interfaces for both Quantum Espresso and VASP. So if there's any users or anyone who is actually doing polarization calculations, I'd be happy to chat and help you get things set up. And our preprint should be out soon, where we go into all the very scary mathematical details that I did not explain here. And I want to start off by thanking both my practicum advisor, Jeff, and Francesco, who I worked with very closely during my practicum at Berkeley. And I also want to thank my current advisor, Julia, and Youngkin at UChicago. I think because of the fellowship, my advisor was very excited for me to continue working on this project even after my practicum, and being able to work on it across multiple research groups really made the code much more user-friendly. And my second part is I want to thank the DOE. I really had such an incredible and am having a great time in grad school, and I attribute a lot of that to this fellowship, not just the ability to do the research that I want, but also all the people you meet along the way. So with that, thank you, and I would like to take any questions.